Alright folks, in this particular demo, I'm going to showcase some elements of physics that we're going to be playing around with here in the demo after this. This becomes the cornerstone of how the physics will operate in your particular projects and your understanding. Now, I am not going to, however, let me go ahead and close my launch here. I am not, however, going to discuss physics materials. And I'm not going to discuss physical materials. Let's do for physical surfaces. This has to deal with controlling elements or objects and their behavior. There is a universal constant that is available on most objects based on most of their elements. So for example, the generic material that you can apply to an object has a certain gravity and physics applied to it, which means that generally what I tell people in Unreal is that all objects, after they fall to terminal velocity, are relatively bouncy. You control the bounciness somewhat through the physics calculation, which is right here. We go ahead and close that and go into physics. We have access to a lot of elements of how the physics in the game is supposed to work. We're going to stay away from this screen for now because this is obscenely complicated for what the physics is going to do for our beginner class. But physical surfaces in conjunction with the physics renderer will allow you to make objects that react and respond in whatever fashion that you want to. But it is based on the physical material, not necessarily on the object itself. You cannot make an object so heavy in Unreal Engine where it will not bounce, because the bounciness and the objects, the dynamism of those objects is based a lot on the physical surfaces and also based a lot on these particular settings here. Scrolling to some of these settings, you can actually see some of the settings that is set up, like angular momentum, angular velocity, different kind of thresholds that are set up. All of these settings allow you to control the degrees of freedom, things like optimization for gravity, stuff like that. We don't really have to worry about this per se, because this is not actually a function that is going to affect how our physics is going to work in this particular demo. For example, the global bounciness is set to 200 for the bounce velocity, which applies a certain bounciness to just about everything in the scene, which might not be ideal. If you want everything to be a little bit more still, you can set this to like 10. But we're not going to worry about this. We're just going to let the physics kind of figure itself out. And another thing that I wonder if PCM is still in here. Yep, enable PCM is on by default, which is good. Let's find the setting so I can know that it's being generated. It should be under simulate. Hold on, I must be crazy. Engine physics simulation. It's going to be under advanced settings. Yep. So the default settings are going to work just fine for these particular demos to showcase what's happening. So I'm going to go ahead and close this for now. But understand that there's a much, much larger world for modifying the physics of an object or your objects by changing the way that gravity works in terms of calculations in your engine. I'm going to go ahead and close this. Double check my recording here. All right, we're still good to go. Let's go ahead and talk about some of these physics properties before we move on. So as far as a high concept understanding, given the increasing complexity of meshes and their calculations that are used to drive physics, generally speaking, objects inside of Unreal will use either what's called physics body instances, or boxes, or spheres, or capsules, or hulls that is used and will be used for physics information. Those things are really important in relation to what the physics of the object is currently doing. Now this ties together with collision, We'll talk about collision in the future. And I know we talked about a little bit more. We talked about a little bit of collision at the beginning of the course, but it's still really important to understand that those elements are still really important. And we'll talk about those elements as we go. For example, I'm going to click on the box here, and I'm going to go ahead and open up its physics panel here. And we're going to take a look at what these do. We have mass in kilograms, which is basically the mass of the body in kilograms. Yes, I know. I'm sorry. It's not pounds. You got to learn metric. We have angular dampening, which is the amount of drag force added to reduce an angular movement. So if an object is spinning, that is what angular movement is. Linear dampening is the amount of drag force that is added to reduce linear movement. Think of it as like the anime slide back, where a character blocks and then slides back. Their feet have a certain amount of dampening. Yes, I know. Dragon Ball Z fans, you're welcome. Naruto fans, I hate you. I don't actually hate you. It's Boruto now, right? Ugh. Enable gravity allows an instance to recognize that gravity is supposed to be calculated on it and has a certain amount of constraint applied to it. Do I want to talk about constraints? No, I don't. Let me double check something here. I don't have to worry about double-sided geometry or anything that's not in these settings anymore. So I'm going to go ahead and close constraints here. Don't have to worry about any of these elements. So basically, what we are able to manipulate inside of physics here, and these are probably the most important up here, is that we can control where the mass, what the scale, whether or not an object is behaving in a certain way. I generally don't touch these for the time being, but they allow us to control what this object is doing at rest when this object is waiting for some kind of physics input. Let's go ahead now and talk a little bit about some of these properties and talk about what is happening to them when they're actually running. The first one that we're going to talk about is the idea of simulating physics. If an object, for example, these boxes, have their mobility set to movable and it has simple collision and physics are enabled, you can check that flag to turn it on, as you guys saw, and then the object will attempt to generate physics during actual play mode. In my current example, I have play mode selected, and I have from current camera location, and I'm just going to hit play. It might actually be a little easier if I just simulate. There we go. We see that on every frame, the calculation of the physics is happening to these particular objects. Why? Because these boxes are instantiated to simulate physics, but they don't weigh anything in kilograms. But we see that once they hit the ground, they have a certain behavior to them. In this particular example, if I switch to play mode, I can go ahead and pick these objects up because they don't have any weight. And if I hit right click, I can fire them away. And if I kind of walk through them, they're going to not resist me as I kick them around. There's a little bit of collision involved, obviously, but as I kick them around, you see what's happening. This element is to simulate a skeletal mesh. Skeletal meshes, which we'll talk about in the future, can only be created with external software or if you use the rigging toolkit inside of UE5. But typically speaking, the documentation would prefer that you rig characters outside, either DAZ or 3D Studio Max or Maya. However, their collision is going to be set up in Unreal Editor. So when you import a physics asset, when importing a physics asset, you can automatically create an object when you import if create physics asset is selected. For those of you guys who remember that, let's go ahead and let's see if I can actually get that to work. Let's see if I can find something. Let me do that. I'll grab a tessellated plane here, and I'm just going to mock, oh, wrong thing. I'm going to go ahead and mock import it here. I'll put this in this My Stuff folder. Go ahead and open this up here a little bit and have a look. Actually, you know what? Let's cancel this and I'll grab something else. Oops, wrong thing. I'll grab an actual FBX file here. I'll dock that temporarily so I can drag this in. Let me get rid of this. It's an animation, unfortunately. Let me grab something. There we go, I found an asset that I could use. So for example, we're importing a skeletal mesh from this particular character. I have a character that I have for this particular example here. And we are importing the mesh, and it's going to be looking for a skeleton. In this particular case, we can always apply a skeleton if we already have one, but in this case, we are importing skeleton from the skeletal mesh. When importing our physics, this is what is going to control whether or not the skeleton is going to import its own particular computations or if it's going to rely on the skeleton. Typically speaking, you want to make sure that when you import a physics asset or you import a skeletal mesh, the create physics asset is going to be turned on. Now, we're not going to talk about skeletal meshes too much. Again, I will just kind of showcase this in an example. I'm going to cancel that because I don't want to actually load that, and I'm going to go ahead and close my content browser. But here's a pretty good example of what the skeletal mesh is going to do. Let's go ahead and pick up this little noodly guy, and then let's swing him around. This is actually a skeletal mesh. Let me go ahead and open that up so we can get a look at what it's doing. Open that up. Here's our physics bodies that are imported the moment that we actually import it based on the location of the skeleton. And then we have our actual skeletal rig here, which is comprised of bones. Let me go ahead and close those. We'll cover that in a future demo, but this is again illustrating what the physics is going to kind of look like. Ignore that spike right there. Obviously, when it comes to skinning and weight painting animators, you kind of understand how that works. But you see more or less how this is kind of behaving. This particular example is set up to showcase something called radial force. It's exactly what you think it sounds like. Using a radial force actor, as we can see in this particular example, this uses a trigger volume to trigger a radial force in this particular area. This trigger volume is set up with a blueprint to trigger a radial force. So you can trigger something called a constant force or impulse, which is kind of like starting from zero and then adding the force on an event. Now, impulses need to be fired from a blueprint, so I'm not going to show you this particular blueprint, but they apply all their forces all at once. In this particular example, we'll showcase kind of how all of these forces work, but watch what happens. In this particular blueprint example, a constant force is going to be added the moment that you start overlapping that box. Remember we talked about volumes? Let's do that again. That was actually kind of fun. Again, impulses only fire for a moment, whereas constant forces continue on until they actually complete or resolve. As you can see if I can get this to go back. There, drop it. So as you see, this is actually still receiving a little bit of physics force. Let's see if I can get this to move up. Does everybody see how that kind of moved to the right? A little slightly. See? So there's a constant magical force being applied to this as long as I'm inside of this box. Let's go ahead and reset that once more and have a look. A constant force is applied the moment that we actually step in this box, and that is our radial force and our impulse. Probably the one that most students have the most fun with and is the most hilarious is something called a physics thruster. A physics thruster is a special kind of physics actor. Yes, it looks like a rocket. Yes, I know. Physics actor that you can place in the editor and then pair it to a physically simulating object, making the object, whatever that object is parented to, receive the force from the thruster. So this thrust propels the physics object in whatever its opposite direction. In this particular case, it's negative direction. If it's the positive axis, that is the counter axis. So for example, this is just a thruster, and you get exhaust from the opposite end. So we have this little rocket here, little toy rocket, and attached to it, if you look in the world outliner, is a physics thruster. Now that is not a component, that is just a parented force. Could you make that a component? Yes, you could. But I don't believe physics thrusters are a component themselves. We have our thruster, that's our inherited. Yeah, it looks like you can. So we have a parent-child relationship over here, and we have our thruster instant and our thruster component, which is our thruster overall. And we have our static mesh, which is our static mesh component. Watch what happens if I simulate this. Yes, I know it's ridiculous. This is flying around weirdly because it's crashing into everything, but it has no opportunity to leave the little boundaries that it's created for itself. So you can kind of see how it doesn't have enough centralized mass to figure out. This is almost like watching Kerbal Space Program crash. But the thruster is trying desperately to figure out what direction it wants to go in, with the front of the craft technically weighing less than the rear. It's trying to figure out how to get underneath it. This is something worth playing around with when you have an opportunity in your own time. But thrusters essentially apply the physics of a thrust counter to their location on an object. This is probably the more useful of the bunch. This is what's called a physics constraint. Physics constraints, simply put, are joints. That's what they are. They're a type of joint that allows you to connect two actors together. Presumably, one is going to be simulating the physical, one is going to be simulating the physics, and one is going to be bound to movement. And they also apply either forces or limit. Now, Unreal Engine 5 is really flexible in terms of what the constraint system is supposed to do, that allows designers to make many different types of joints simply by changing some options. This is all the same element, but different types of options in the joint. The engine has a few default joints, like a ball and socket, a hinge, a prismatic, but they only differ in their settings. So you should be able to freely start playing around with any joint type and experiment with making your own configurations. In this particular content example, let's go ahead and look at what's happening from left to right. Let me go ahead and play. The left one will swing freely on its first axis, and it has, we see our rocket kind of flying around over there. It has 45-degree limits on the second, so it's locked on the twist axis. You see that it wants to rest at its twist axis. Let me go ahead and play again. The second one is an angular two-motion swing, where it does have some bias. So you see this is rotating, and this has some linear bias. This one is free on the twist axis, but it's bound on the other one, so it will go forward and back. And this final one is free on all of its axes. This is kind of like a dead hang. These constraints become really important if you have physical elements, for example, like wrecking balls, or if you have like a rope. Although technically a rope could be considered more of a skeletal asset, our little wormy guy over there. But this gives you an idea of how to bind things like chandeliers or destructible objects that don't necessarily need to be removed from the game. This is how we would bind them, using these kinds of physics constraints. Physics constraints are probably the most useful compared to all these other ones, but these, and of course the general physics over there, kind of showcase how physics will work in the particular engine. I'm going to just go ahead and play immediately. Alright. So this is what's referred to as an angular motor. In physics, any physics with an angular motor will spin. But the detail is, how is it going to spin? Angular motors are driven by velocity, right? Angular motors driven by velocity apply constant force and they spin, whereas position-driven, like the one on the right, will attempt to obtain an angle based on the size of the spring and the dampening applied to the spring. This is more like a natural spring, and this is more like... has anyone ever played a skip it? Or this is more like a jump rope. See if I can get this to resolve in a certain way. Come on. There we go. So you see how it has a certain orientation that it wants to achieve, but it's combating the physics of the engine. The physics wants to pull it down, but it wants to go to where it's designated to go to in terms of the motor. So you see that the motor is trying to get it up here because that's where it's designated at. Let's pick that up. The motor wants it to be over here, but the motor doesn't actually have enough strength to move it up there, but the motor is still going to give it impulse bursts to try to get it to move where it's supposed to. And in this particular one, you see that the motor is just like a little rocket booster. Let's see if I can catch it. Gotcha. Now if I let it go, the booster on the actual motor itself will continue its function. A quick edit discussing the angular motor. What might not be immediately clear is that these objects are not themselves spinning. It's the constraints. These elements right here are what are causing the spinning. Right here. This is our angular motor. You see how this is working? And we'll talk about these settings when we're actually rebuilding these, so we have an opportunity to see how they work. This is what is driving the box. The static meshes themselves do not have any ability to generate their own impulse. They have to be impulsed, either by gravity or by a motor. So let me see if I can get this to do some weird stuff. Let's simulate some physics on the red box here. Okay, this might be evil. Whoa, there it goes. Come on. The motor itself is trying to... the motor is having an impact on both of these. That's what... Oh, gosh. That's what's happening. So you see that the motor is driving the movement, not necessarily the red cube. The red cube is the fulcrum. And in that particular example back here, man, we can't even see because it's getting in the way. You see that the red... Stop following me. This red... this red box... This red box acts as the root for where our motor is acting from. And because I've taken away the ability for the motor to act upon this box without being rooted, this red box is now having physics simulated on it. It's no longer acting as a root, and therefore the motor is trying to impact both of these. See if I can hold on to the red box enough to get it to stop moving. I don't think I can. It's moving too fast now. So the motor is actually activated on the red box, but when it's rooted, by having the physics turned off on it, we see that the result is that the motor starts driving the blue box. So like previously, those are angular motors. Let's go ahead and play so we can see it. Those are angular motors. These are linear motors. Think of these more like springs. Boing. Boing. This one acts more like a spring because it's denoted by its position. So this has a natural position that it wants to achieve. Just let it go. Oing, 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 oing. And this one has a natural speed that it wants to approach at. Granted, it does have a resting point, but it wants to arrive at a certain position at a certain speed. Both of these operate similarly, but the difference being that driven by position is more like what a shock absorber would be like, whereas being driven by velocity is more like what a piston would look like. Yes, a shock absorber is essentially just a piston, but this has more friction and wants to reach a certain state, whereas this one wants to reach a certain velocity before it reaches its rest state. And the last one illustrates breakable constraints. Now, I'm going to have to change this one a little bit because this is actually a little bit busted. Let me go ahead and see if I can fix that constraint. Let's see here very quickly. Where is that value? Let me add a value here, 100. Okay, let's hit play. So for example, breakable constraints mean that once they match or they meet a certain value, let me actually do it again, hit play. They break and that constraint is no longer affected. This one has an angular breakable. So once it actually surpasses the amount of angle that it can withstand, so for example, clicking this one applies no impulse aside of a linear. This one, however, will continue its angular momentum until it supersedes that angular boundary, and then it will break. It's the spinning that breaks it on the angular breakable. It's the linear force that breaks it on these constraints. These are all options within the same controller. These are your typical physics constraints. Yes, they change a little bit, but you get the idea for how they work. Each of these individual constraints can be controlled differently depending on what these settings are in the details panel. There is no other place to change them. It's not wizardry. The only difference being is how these objects are connected in the world outliner. So for example, we have this cube here, we have a joint actor, and then we have another cube here. The parenting and childing is done here. As opposed to doing it inside of the world outliner, the physics constraints and the joints themselves have physical constraints that we can put in here. Now, it is limited to just 2, so you can create chains, but it is one of those things that, at least for this particular demo, let's keep it simple to 1 object, 1 sub-object, and 1 chain comparisons so that we can actually build these together. So in the next demo, what we're going to do is we're going to rebuild these so I can explain to you how they're built, explain their realities, explain how they function, and then we'll go from there. All right, I'll see you guys in the next video. This has just been an illuminating video on how each of those forces work and how physics operates in the Unreal Engine.